Alright, let's get back to doing some more of these derivative problems that you were working on. So we did the first four in the last video, so we'll try to do the rest of them in this video. The next one we're looking at is f of x is 3x plus 2 divided by x squared minus 4. So if you were to evaluate this function, the last step would be to do the division. Remember, a horizontal line is a fraction symbol. It's also a division. It's also a grouping symbol. So it says find the numerator and denominator separately and then divide. So the last step is division. So the rule we use is the division rule. The answer to division is called a quotient, so we really call that the quotient rule. So this is the way the quotient rule works. It's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. So we have the denominator x squared minus 4 times the derivative of the numerator minus the numerator times the derivative of the denominator, that's the x squared minus 4 there, over x squared minus 4 squared. So the derivative of the 3x plus 2 is 3, the derivative of the x squared minus 4 is 2x, so now we have the correct answer. We want to clean it up a little bit, so we're going to leave the bottom like it is for the moment. We're going to distribute in the top and make it 3x squared minus 12, and then make this negative 2x times 3x plus 2. So we're using our distributive property. The 3 times the x squared was 3x squared. The 3 times negative 4 is negative 12. Here we have negative 2x times 3x is negative 6x squared. And negative 2x times 2 is negative 4x. Combine like terms. 3x squared minus 6x is negative 3x squared. Then you got a negative 4x and then minus 12. Now typically we like to have our fractions in a factored form. In fact, in general, we kind of like our derivatives in a factored form when we can get them that way. Let's see here. There we go. We can see the rest. So in the top, the only thing I can do is factor out a negative 1 as long as I only want to use integer coefficients. But in the bottom, x squared minus 4 factors as x plus 2 times x minus 2. So that's x plus 2 squared times x minus 2 squared. So notice that the derivative and the original function for that matter were both undefined when x equals negative 2 or x equals positive 2. And over here on the graph, sure enough, we see vertical asymptotes at both of those places in both the original function and in its derivative. We check that with a calculator by putting in the original function, 3x plus 2 divided by x squared minus 4, in y1. Remember to put parentheses around the numerator, the entire numerator, and around the entire denominator anytime you have a fraction like that. y2 in all these examples will be set up as a numerical derivative of y1 with respect to x, evaluated at x, and so that will be math 8 on a TI-84, and then put in y1, which is variables, right arrow to y variables, function y1, comma, x, comma, x. The comma, find the 7 key and look one above that, you'll see the comma. And put that in for y2, just leave it the whole semester. It's a great thing to just leave it in there. Toggle it on and off as you need to by putting your cursor on the equals and hit enter. Then we put the answer here, the formula that we have at the end. Again, remembering to put parentheses around the entire numerator and the entire denominator. Check the table, make sure you're checking just y2 and y3, and notice that those agree, so that's our check. That the numerical derivative, which is really a symmetric difference quotient, is the same as the actual derivative, which is what you have here. Of course, these are all approximations, but they are the same. Now, this window that's under the black there is a negative, so this is negative 10 to 10 on both x and y. Just a zoom standard actually does this. And that gave us a decent graph. It's a little hard to see, but both graphs are looking pretty close to each other right here in this part. Then the darker one here and here is the original function, and the derivative is here. And this middle part, the derivative comes up and then back down. So we can see that what we have there. And you can kind of look at the derivative and the original on the graph and see some interesting things. So for example, notice that the original function over here is decreasing and concave down. Since the original function is decreasing, the derivative is negative. Since this is concave down in the original, the derivative is decreasing. They both have asymptotes at the same places. The original function is decreasing on this piece, so its derivative is negative. It switches from concave up to concave down somewhere right in here, and that's where the derivative has a maximum. And then over here in this last piece, the original function is decreasing, so the derivative is down here negative, and the original function is concave up, so the derivative is increasing. So all those things agree with what we know should be happening with the graphs. Okay, let's move on to the next one. F of x equals 4 to the power 3x squared minus 5x plus 1. Again, what we want to do is to start by pretending we're evaluating this function and plugging in an x value. What would you do? The first thing you do is square the x, then you multiply by 3, then take negative 5 times the original x, then add and take 1, and add those three things together. And then you would take 4 to that power. So the last step is raising 4 to a power. So what you're doing is you're taking the derivative of 4 to the u power, where u is the 3x squared minus 5x plus 1. Whether you write it down or not, you're doing this substitution where you let u be the power. So it's the derivative of 4 to the u. The derivative of that then is the natural log of the base, 4, times the original 4 to the u, and then you're taking the derivative of the u. Of course, the u is the 3x squared minus 5x plus 1, which the derivative of that is 6x minus 5. Substitute back in what u is, and you have the final answer. I pulled the polynomial closer to the front, so I have the constant in the front of ln of 4, then the polynomial 6x minus 5, and then I put the exponential last. There are some other orders you could do that would be perfectly fine. So that's the way I would write the final answer, which I put in y3, the original in y1. Watch the parentheses there. You can see it here. Again, as always, numerical derivative in y2, and we check that the tables match for both of those, of y2 and y3. Make sure you're not looking at y1, you're looking at y2 and y3, and they do check out. A little experimentation on an appropriate window led me to the window -2 to 2 on x and -100 to 100 on y, and we see this. It looks like the original function is decreasing and then increasing. Somewhere in here it has a minimum, and that same place is where the derivative has a 0, crosses the x-axis. Over here on this part, the original function is decreasing, so the derivative is negative. Over here past that point where the minimum is, the original function is increasing, so the derivative is positive. It looks like the whole thing is concave up on the original, so the derivative is increasing the entire way. Next one, number 7. F of x equals 3x to the 5th minus 1 to the 25th power. Again, if you were evaluating this, you would plug in an x, you'd raise it to the 5th power, then times 3, then subtract 1, and then finally the last step would be raising to the 25th power. So what you're doing is taking something to the 25th power. Let u be that something, that variable base. U equals 3x to the 5th minus 1, and we're taking the derivative of u to the 25th. Now it fits the pattern for a power rule. You know how to do that. It's 25 times u to the 24th. Bring the power down, subtract 1 from the power. So the power brings down as a coefficient multiplied by the original base, and then you subtract 1 from the power rule. But then since we did a substitution, we have to use the substitution rule. In other words, the chain rule, which says we have to multiply by the rate. Okay? Notice there is no rule that says we put the derivative in the place here. The rule says this is 25 times u to the 24th. Not u prime, but u. The u prime is out here multiplied by it. So the chain rule has us multiplying rates, not substituting rates in other rates. Okay, be careful about that. So u is 3x to the 5th minus 1. The derivative of that is 15x to the 4th. Multiply all that together. 15 times 25 is 375. U is the 3x to the 5th minus 1 to the 24th, and then we still have this x to the 4th, which I put in between here. And so there is the final version. Okay, so we can graph this. The original one, that's the little box is over parentheses there. 3x to the 5th minus 1 to the power 25th, numerical derivative in y2, the actual derivative in y3. We check that y2 and y3 match. They do. Here I graph from -2 to 2 on x and -100 to 100 on y, and we see the shape like this. It looks like the derivative is increasing the whole way, and the original function is increasing the whole way, so the derivative is always positive, or, well, there's one place where the derivative is 0, and the one place where the derivative is 0, that's going to be the place where the original function, let's see, has an inflection point, as it turns out, not a minimum, because the second derivative is also going to be 0 at that point, as it turns out. So when the derivative here is 0, the original function has an inflection point somewhere in here. The derivative is actually 0 when x is 0, and here as well. Okay? You know what? We might examine that a little bit more closely, because the derivative is actually 0 at two places here. We could actually have a max and a min in there. Actually, looks like maybe that is what's happening. Maybe we need to look at this graph a little bit more closely right in there. We could actually have a max and a min there, and the second derivative may be not 0 at either one of those points, but somewhere in between. So let's take a look at the graph a little bit more closely. Okay, so we'll get back to the window in a minute. Let me just turn this off for the moment. Okay, 3x to the power 5 minus 1 to the power 25. And then here we want to put in 375 x to the 4th times 3x to the 5th minus 1 to the 24th. Okay, so we think there might be something interesting happening really closer to the x-axis. So let's just start with the zoom standard. And here's the original function. Okay, let's zoom in. Let's zoom in a little more closely right there. Let's see if I can stop it. Okay, start with the zoom box, and let's zoom in kind of close here and see. I'm just going to have to finish graphing for it to let me do this. Okay. So right in here it looks like there's some interesting things happening. It's a little hard to see exactly what is happening right in there. So let's look a little more closely here. So I could just enter some x values and y values in my window, but I'm going to use the zoom box this time feature to allow me to box off a portion of the graph that I want to look at more closely. I'm interested in what's happening right in here. I was kind of lost on our other picture. Should have hit enter. Try again. Alright, so this is the original function coming in first. Looks like maybe an inflection point there at 0. And then looks like another inflection point over here, perhaps. So it looks like maybe the derivative is 0 here at 0, and that means we must have either an inflection point or a max or min here in the original. It looks like it's going to be an inflection point. And over here the derivative is 0, and so is the original function. That's it. This one over here is when 3x to the fifth minus 1 is equal to 0. So that's the fifth root of 1/3 is right there. And it's a minimum on the, both of these are minima on the derivative, and that makes them inflection points on the original. So let me get this closer up version here, and I'll make this darker so we can tell them apart. So in fact, f prime is at a minimum twice, and the derivative, f prime is 0 twice, which is where it's at a minimum, and then those are the same places where the original function has an asymptote. Okay, interesting. Notice that even though I didn't really see it very well in my first picture I had, looking at the formula led me to investigate this a little more closely. Okay, so the inflection points of f of x when f prime of x is at a minimum at x equals 0, let's see if I can, and x is the cube root of 1/5. Okay, I may write that in later. So the cube root of 1/5 right here, and 0 right here for x, and we see that some interesting things happening there. So two inflection points. Notice in between over here to the left of 0, the original function is increasing concave down, so the derivative is positive and decreasing. Between 0 and there's also actually an inflection point right here somewhere where the derivative is at a maximum. There's also an inflection point. So between these two, the original function is increasing concave up. So since it's increasing, the original is increasing, the derivative is increasing. Since the original is concave, since the, let's say this right, since the original function is increasing, the derivative is positive. Since the original function is concave up, the derivative is increasing. Then the original function is still increasing right here, so the derivative is still positive here, but the original function is concave down for a little while, and so the derivative starts to decrease. The derivative hits a minimum here, and the original function hits an inflection point, and they both hit 0 at the cube root of 1/3, which is right there, and then from there on, they're both increasing concave up from there on out, and positive. So notice how we can use the graph of the derivative and to tell us a lot of things about the formula for the derivative, for that matter, and the table, all above, to tell us something about the shape of the graph of the original function, and vice versa. Okay, a couple more, 3 more of these. Okay, so f of x is the natural logarithm of the absolute value of 2x squared minus 5. So notice the last thing you're doing was taking the logarithm, but we do have a rule for logarithm of the absolute value. So if you just let the u be the 2x squared minus 5, we're doing the derivative of log of absolute value of u. That we do have a rule for that. It's 1 over u times the derivative of the u. U is 2x squared minus 5. That derivative is 4x. And of course u is 2x squared minus 5. So we get 4x over 2x squared minus 5. Because the absolute value, we don't have to put a restriction on this. Of course, when 2x squared minus 5 is 0, that is when x is the square root of 5 halves, plus or minus the square root of 5 halves, then we're going to have the derivative as undefined. The original is also undefined there. Okay, and the original is let's see, is that true? The derivative, yes, that's true. The original function is undefined there because that this part right here would be 0, and the absolute value is 0. The log of 0 is undefined. So the original function is undefined right here at those points there. Actually, we have, I really think this probably has, yeah, definitely it has, this graph's a little misleading. The original actually has vertical asymptotes right there, and so then the derivative is there. So I said it has corners, but that's not true. It looks like it from the picture. We'll say they both having vertical asymptotes. Okay, so let's see what else we can notice. Well, first of all, I checked it by plugging in here. And, of course, again, if I would plug in negative square root of 5, let's see, plus or minus the square root of 5 halves, both functions would be undefined. As I look at y2 and y3, it does seem to check out there. Okay, and let's see, what else do we see? We see the original function on this piece is decreasing concave down. So, since it is, since the original function is decreasing, the derivative is negative. That checks out. The original function is concave down, so the derivative is decreasing. On this middle piece, well, on this next piece, from here to here, the original function is increasing, so the derivative is positive, but it's concave down on this whole piece, so the derivative is decreasing. Right here at 0, we have a maximum in the original function, and that's where the derivative is 0. If you can see, that's when the derivative is 0. That's when the top is going to be 0. Okay, and that's going to be where we have a maximum of the original, and then this is decreasing after that, so the derivative is negative. On the last piece, which is coming up this way, the original function is increasing, so the derivative is positive. The original function is concave down, so the derivative is decreasing. Okay. Let's see what we have here. Okay, a couple more. F of x equals ln of 4x minus 11. This time we don't have an absolute value. Again, we do a substitution of what's inside the ln. It's 4x minus 11, so it's the derivative of ln, natural logarithm, of u. And so that's 1 over u times the derivative of the u, but we have to make sure u is positive. So we have to restrict the domain to only where u is positive. So the derivative of 4x minus 11 is 4. So this is 4 over 4x minus 11. Now if we just wrote it that way, it would look like anything would work except for 11/4. Okay? So of course when 4x minus 11 is greater than or equal to 0, then x is greater than or equal to 11/4. And of course that's what we have to restrict to. So when I look at my graph, basically I'm going to look to the right of 11/4. and we see the original graph actually has you can't see all of it. It should come down this way. A vertical asymptote coming up across here. So the original function is increasing, and so its derivative is positive. The original function is concave down, so the derivative is decreasing. Checked y2 and y3. It checks. Looks like everything's checking out there. Last one for this set. Number 10. Okay, number 10 is going to use our generalized version of the power exponential rule. Let's see if I can get it to show on the screen here correctly. F of x equals x to the power x minus 2. So basically what we get is we get the power rule plus the exponential rule is the way it works for the derivative. So for the power rule, we take the power, whole power down and make it multiplication, times the original function, but you subtract 1 from the power. X minus 2 minus 1 is x to the, it's the x minus 3 for the power. But then you have to take the derivative of the part that would normally be the variable in the power rule, the base, the derivative of x. Plus, for the exponential rule, we take the natural logarithm of the base times the original function, just like it is, but then times the part that would be a variable normally in the exponential rule, which is the exponent. Now, derivative of x minus 2 is 1, the derivative of x is 1, so those parts kind of go away. They both have, we take these x's to the smallest power, which is x to the x minus 3 power, so we factor that out, and when we divide this by x to the x minus 3, that cancels and we're left with x minus 2. This one we're left with the ln of x and an x to the first power. Now let's just check out the distributing. If we take x to the x minus 3 times the x minus 2, we get the first term, and the x minus 3 times another x gives us x minus 2 times the ln of x gives us the second term. So this is the correct way to write that. As usual, we can check it. Unfortunately, you see a little box there. That should have an x there. It's being covered up. So that's x to the power x minus 2. And then the numerical derivative in y2 and the final answer in y3. And we check y2 and y3. Yep, they're checking out. That looks great. Okay, and for this one, normally in a function like this where we have variable base and exponent, we're only going to define it for positive values of x, although I guess some negative values would make sense. We're only going to look at it for positive values of x. And so we look at the graph here and we see then the original function is here, the darker one, and the derivative is here. The derivative, if x is 0, it's undefined. So looks like x is gonna we're gonna have to be looks like we're gonna have to be at least 2 for this to be defined, for both the base and the exponent to be positives there. And so we see a shape like this. Let's see. Looks like the derivative, there is some place in here, I can't really tell what it is very well, but there's some place in here where the derivative is 0 and the original function has a minimum somewhere right in here. The original function looks like it's concave up everywhere, so the derivative is increasing everywhere, and okay, this part the function is decreasing, so the derivative is negative. This part the derivative is positive because the function is increasing. Somewhere in here, right at the minimum of the original function, the derivative is actually equal to 0. Not easy to find exactly what that is algebraically, but we could approximate it with the calculator. So, there we go. With this video and the last video, that gives you 10 good examples of finding derivatives. We actually used every rule at least once, most of them multiple times, that we've learned so far. And we've also practiced checking this in the calculator. So notice that with a TI-84 calculator or something similar to that, it doesn't tell you the answer, but it does allow you to check any derivative problem. And we also kind of reinforce some of our ideas about what happens to the graph of a derivative versus how that compares to the graph of the original function. In the next set of videos, we're going to do some more challenging problems. I'll give you a sneak preview here, where we're going to look at these functions here. There's 20 examples, 20 more examples. Some of these are similar to the last ones. Some of these are a little harder in a couple cases, but mostly similar to the last ones. But this time I'm asking you to find the first derivative and the second derivative. And the second derivative on these, let me warn you, some of those get a little bit more involved. But we get several things we can look at to find the first derivative. Some more interesting things for the second derivative. You can check these all in your calculator as you go. And then we're going to look at graphs of all of these. Also in these, I ask you to find the formula for a tangent line, a specific tangent line as well. So, if you want to go ahead and write these down now, or you can look at the next video and write them down, and then go on and practice some more problems there. So this should give you plenty of examples to look at.